All right, kiddos, let's talk about reaction coordinate diagrams now. So this is going to be looking at endo versus exothermic reaction charts
Okay.
and just kind of interpreting what they mean. So the first one here is we're looking at an endothermic reaction. Okay. So what we can see here is we can see the potential energy is the y-axis.
Okay.
The reaction pathway as it moves across is on the x-axis. So what I want to point out here is this. Our reactants are right here, our products are up here. So obviously the energy of the products is higher than the energy of the reactants.
And that delta H shows how much higher.
Right. So this right here, this delta H, this value tells us that that is how much higher those products are than the reactants. This is an endothermic reaction because we had to add energy in to get to those products. One thing I also want to point out here is as we trace, let me go ahead and clear this, as we trace that curve and we see how we get from reactants up to products, we actually end up with a little bit more energy than the products end up having at the top at that thing called the activated complex. So how do we get energy from the reactants all the way up to that activated complex? Well, that is the energy of activation here. That's what this whole thing represents right here.
And that's the kinetic energy of the reactants when they collide has to reach a certain level for the reaction to proceed, to overcome the repulsive forces.
Right. So if we're thinking about the energy required to activate a reaction, we think about it like a roller coaster. If you're on a roller coaster and you're moving this way and all of a sudden the roller coaster stops when you get right there, are you going to be able to go down the fun part?
No.
Over here? No. You're going to actually end up falling back down. So you have to get enough energy to where you can get all the way up to the peak here before then you can go down.
And then form your products.
Right.
Yep.
So that's endothermic.
Okay.
Let's then go on to, and see, there we go, energy of reactants is less than the energy of products. Now we look at exothermic. Now this looks a little bit different. It's just the opposite, right?
Yep.
What's one thing you notice right off the bat? Anything about it?
The reactants have more energy than the products.
Right. The reactants have a lot more energy. The reactants energy is up here and the products energy is down here. And so that delta H that's right here is still represented by the difference. But in this case, since it's exothermic, it's going to be negative.
Right.
All right.
And you need a lot less activation energy for an exothermic reaction.
That's the other thing I was getting to. So if your reactants are here, you only need this much activation energy to get to this top right here, to get to the top of the hill. So this is a much easier roller coaster to be on because you only need to get from here to here before you can then really enjoy that.
If you enjoy that.
Well, I enjoy that sort of thing. I love roller coasters, but that's just me. So the activation energy is a lot less because generally these reactions want to happen.
Right.
And they only need a little bit of a push. So let's wipe that here and just make sure that we hit everything. We got the exothermic reactions and everything like that. And then there's a little reminder down there that the heat of the reaction is equal to products minus reactants.
Yep, so hopefully this makes it a little more clear how to do the calculations.
Right.